Alright, so let's say that we have an object that's somewhat irregularly shaped. And it's got a mathematical formula, though. And somewhere in the middle, it's cut in half. Perhaps like that. Now, a person on the left is going to push. So they're applying a force. And we've got two pieces to it, M1 and M2. They give us the area mass density of the shape being 1 kilogram per meter squared. We know the force applied is 200 newtons. And we're going to use no friction for this example. We have to use calculus to find the normal force that exists between the pieces. So basically, how much force is there between M1 and M2? Now, the formula that the shape follows is y equals the square root of 16 minus x. So we can use that to do our integration to find the area. And then we can use the area mass density to find the mass of each piece. Alright, so let's see if we can put it all together here. Let's find the areas first. So we can find the area of piece 1, which would be an integration from 0 to 8 of the square root of 16 minus x dx. It does require a u substitution, it's called. So what you do is you let the u equal 16 minus x, because we want to transform it into a simpler integration. And it would be simpler if we were able to get rid of all that stuff under the square root and just replace it with a single variable. But that variable is a function of x. And so, to be clear here, my limits are x values, not u values. And my differential is still dx, so you can't integrate yet. We would do du over dx, find that. It's going to be -1, so therefore du equals negative dx, or in other words, negative du equals dx. And in this technique, you're supposed to take the dx out and replace it. Alright, so you could get x equals 0 to x equals 8, radical u times du, and then put a negative out front. Because basically what I did was I plugged in the negative du. Alright, now you can find that antiderivative. So u to the 1/2 du with a negative out front. It's going to be u to the 3/2 divided by 3/2, which would be times 2/3. And then we want to go from x equals 0 to x equals 8. See, I like to keep it in there that I'm using limits that are x values and not u values. What I'll do is I'll put back in my definition of u, which was 16 minus x. And now, see, I brought the x back, so I can still use the limits that I had kept in there all along of just x equals 0 and x equals 8, because now I have an x variable to plug them into, is the idea. Alright, so you plug that in. Let's see what we get. I'm getting 27.6. And that'll be meters squared. Alright, so M1, according to this analysis, is 27.6 square meters. You want to just check that and see if it's reasonable. I mean, if we were to just take this rectangle right here as an 8x4 rectangle, so that would be 32 square meters. So yeah, I think it's pretty reasonable. All right, then we want to find M2. You could set up a new integration going from 8 to 16 for that. That's one option. That would be A2, but it may actually be faster to find the whole thing. So A1 plus A2 could be an integration from 0 to 16. We'll integrate from, I'll do 8 to 16 first. All right, looks like our small piece is going to be 15.1 meters squared. And if we do the whole thing, we get 42.7. All right, so (15.1). Now that I have the areas, I want to turn them into masses. So M1 is sigma times A1, and M2 sigma times A2. Alright, so let's plug in. Use our area mass density multiplied by the area. So that's obviously just going to be 27.6 kilograms. M2 Great. Now that we have the masses, we could definitely find the normal force between them. I'm just going to use that simple approach of the force of 1 on 2 will be the fraction. It'll be the fraction of the cart, the thing that's being pushed, divided by the total. Okay, so see, 1 is responsible for pushing 2. So this is F of 1 on 2 that I'm trying to find. That's the normal force. So we would get that. Let's put our 15.1. Okay, 15.1 kilograms over the total, which I said was 42.7. And then the person's pushing with 200 newtons. F1 on 2 therefore is 70.7 newtons. Alright, so just to complete the free body diagram for the other block, the forces are the force of the push from the person, and then there's a reaction force F of 2 on 1, it's called. That would be the resistance that the front block provides. So apparently the person's going to push with 200 newtons, but only 71 or so of those newtons ends up getting applied to block 2. And our reaction force has to have the same size of newtons, but opposite in direction. That's Newton's third law. And so the third law just says that the force of one object on another will equal the opposite of the force of that second object back on the first. That is Newton's third law. But one thing to keep in mind about Newton's third law is it has to be one system interacting with another system. So if I treat block 1 as one system, and then treat block 2 as another system, then they can interact through Newton's third law. Alright, so this is system 1, and this is system 2. So you have to have, one of the Newton's third law pairs acts on system 2, and then its reaction force acts back on system 1.